Buckle up. It's time for Lagrange remainder. Here we go. Whew. Get ready. Now, let me tell you about Lagrange remainder. This is the last part of this unit. Last one. All right, we made it. We made it to the ultimate lesson for Taylor polynomials. So a while ago we talked about alternating series error, like how we can use the alternating series error to give the worst case scenario for any alternating series estimate. So wherever you stop with an alternating series, the very next term the error involved in that estimation is less than whatever that next term is. Okay. Now, it doesn't always work, right? There's more than just alternating series error, because there's more than just alternating series. So with an alternating series, you see it down there, the bouncing back and forth. So if I stop adding after 3 terms, right, the distance between the real sum and that third, the third partial sum, that exact error, so the difference between s minus s sub 3, that's the third term remainder. That's always less than whatever that next term is. Okay, so if I stop after n terms, that's the that error is less than the very next term in the series. Now, not all series are alternating, right? So let's just take, for example, an all positive series. So a series that adds terms forever, right? So if I add and I add and I add and I stop adding after 3 terms, right? There's no telling. There's just no telling how far away I am from the actual sum. And certainly that very next term is not going to be enough. So that very next term in the series is actually less than what that error is. So for an all positive series, there's really just no reliable way to figure out how close we are to the actual sum just by looking at the next term, right? You just can't do that. It's means that there's another form of error. It's called Lagrange error, the Lagrange error bound. Okay, and for many, it is just like cuckoo for Cocoa Puffs. It's just crazy. Alternating series error, way easier, way easier. Just start praying right now that is the error that the AP exam asks you about. But there is this other type of error that is worth talking about. So we need to know where it comes from. All right. So how are we going to restrict the amount of error with an estimation, right? That is the point, right? We know that there is error involved with these Taylor approximations. But how much error, right? We want to limit the size of the error. We want to give an approximation that we know is within a certain amount of the actual sum. If we don't know what the actual sum is, we need to be able to say that it's within this amount. Right? That's pretty important. All right, so it's going to stem, this Lagrange error is going to stem from the mean value theorem, this magical mean value theorem, which way back when we used the mean value theorem to prove the fundamental theorem of calculus. If you remember that, this magic point along the way. Well, we're going to use the mean value theorem again, and just stick with me here. You can jump to the examples for sure, but stick with me here because this is important to see where it comes from. So I'm going to make a long story short and just skip ahead a little bit. Okay, you can check all this out. I'll give you the notes and everything. All right, I think this is where I want to start. All right, so we're going to start pretty deep into the derivatives, right? So you can say that the mean value theorem says that the average slope between 2 points, right, just a straight line slope, there is some point in between where the derivative, where the instantaneous rate of change is exactly the same, right? As long as the function is differentiable, that is. All right, so we can just go deeper and deeper and deeper. As long as the second derivative is differentiable, then there's a third derivative point, right, in between the second derivative graph where the third derivative is exactly the same. And you can just go deeper and deeper and deeper into the derivatives using this idea of the mean value theorem. Okay, so let's go all the way down to the third derivative. So f triple prime at c, this magic point where the slope at c is equal to this average rate of change between 0 and some x value. All right, just stick with me, okay? So we're going to do some algebra here. So we're going to multiply both sides by x, and then we're going to solve for f prime of x. So we want to isolate f double prime, we want to isolate f double prime of x. So you can see after a little bit of algebra, adding f prime of 0, we get this second step here where f double prime of x is equal to this critter. Well, then we're going to integrate both sides. So the integral of both sides, right? Let's see. So the integral of f prime prime, well, that would be f single prime. The antiderivative of f double prime of 0 is, careful! That's a constant. So we're just going to tack on an x. And then here we're going to integrate the x. So that's going to be x squared over 2 multiplied by that constant sitting next to it plus some mystery constant. All right, so that's where I get this from. So f prime of x, and you can see all this stuff. And I use k because the c would be doubled up, and I don't want to do that. Okay, so now I have to know, well, what was the initial condition? The initial condition at 0 is f prime of 0. So the initial condition, I don't know what f prime of 0 is, I just know that that is the point on f prime graph that is at 0. So subbing in 0 everywhere, so 0 goes in for x right there. That is equal to f prime of 0. Well, that means k is equal to whatever f prime of 0 is. Okay. So f prime of x is f prime of 0 plus f double prime of 0x plus f triple prime at c divided by 2 times x squared. All right, so we're going to keep going. Now we can integrate again to get back up to f. So we'll just integrate again both sides and just kind of repeat that process. So here we go. We get the integral of f prime is f, and then the integral over here, f prime of 0 is a constant, so it gets an x tacked on. This is a coefficient times x, so f double prime of 0 over 2x squared, and so on, right? Just using the power rule. Well, there's an initial condition to contend with because we have this constant of integration. Well, that's just going to be at x equals 0, the point is f of 0, the y value is f of 0. So we'll sub all that in. So 0 goes in for x, all these little pieces, and then that's equal to f of 0. Well, then all these pieces just wipe out because they're all being multiplied by 0, so that means k is f of 0. So let's take a look at the result. The result is that f of x, the function f of x, is f at 0 plus f prime at 0x plus f double prime at 0 over 2x squared plus f triple prime at c over 6 times x cubed. Now, if you look carefully, you might notice something interesting pertaining to Taylor polynomials. Now, if you're here watching this video and you're like, oh my gosh, this channel is amazing, talking about calculus, I got to find out more. Well, you know what? You can just hit the subscribe button, and then that notification bell will alert you to any new videos. You don't want to miss out on this. This is awesome. Well, check it out. F of x. Now, these first three terms, those are the beginnings of the Maclaurin polynomial for f of x, right? That seems to fit. But then you get this weird term that is f triple prime at c. Now, it's supposed to be f triple prime at 0. That doesn't fit in the Maclaurin polynomial. But we're saying that f of x is equal to. We're not saying that f of x is approximately. We're saying that f of x is equal to. So, is saying that f of x is equal to the first three terms of the Maclaurin polynomial plus this weird error term that's got it's like the weird magic c value, but it looks like the next term in the Maclaurin polynomial. All right. Now, generally, if we continue, if go ahead and do another mean value theorem with the 5th, 6th, 7th, billionth derivative, what you would get is, after all of that integration and all of that substituting the initial condition, you would end up with the Maclaurin polynomial at the beginning plus this weird little term that has the c value substituted in the function, the n plus 1th function derivative. So this is the error term, right? Because we're saying that f of x is equal to. So f of x is approximately the Maclaurin polynomial finite. But then we're adding this red term that is exactly the error between this nth degree polynomial and the real deal value. Are you seeing it? Well, let me share with you kind of exactly what's happening then. So this red term here, there is some magic value, c, that if we dive deep into it, we can get the exact error. Now, we don't want the exact error. We're not going to be asked for the exact error. So we're gonna fudge it a little bit. So what we're trying to do is look at this error term, right? It looks like the next term in the series, in the Maclaurin polynomial, with one twist. The c value instead of the center being 0, okay? So f of x is approximately this nth degree polynomial, but if you add this magical error term, you get exactly the function value. So we're not going to ever be asked to figure out what the value of c is. We're not going to be ever asked to figure out what the exact error is. We're going to be asked to limit the size of the error. So if we're trying to find this magic point, right, existing on the curve, the slope at that point, right, all that mean value theorem. Now what we can do is, instead of finding the exact error, we can go just a little bit bigger, right? If we go just a little bit bigger, then we have captured whatever that value is. If we go a little bit smaller, we don't get it, but we can go a little bit bigger, right? We're trying to get a worst case scenario. We're not trying to get exact, we're just trying to get a worst case scenario. So our error can expand a little bit. We can still catch the exact value. We can't go smaller because we might miss it. Exact would be the best, right? So exact would be the best. Bigger is okay, but smaller is not okay. So the value of that error term, that whole entire numerator, I'm just going to replace with m. All right? So what I'm saying here is that the value m is just the biggest value of that n plus 1th derivative, absolute value, between 0, the center of the polynomial, and x, the place that we're approximating. Like I said, we could go a little bit bigger. So if we just get the maximum value of that function on that interval, we have gone just a little bit bigger than what the exact error would be. But again, that's okay, because we can go a little bit bigger. We can't go smaller. All right, so here is the error term, right? It looks like the next term, but there's that one little weirdo piece. It's that numerator piece, right? The numerator is that n plus 1th derivative at c. That's a weird term. We're saying that spot, that numerator value, is just the biggest value that the n plus 1th derivative takes on between the center of the polynomial and the value that we're approximating at. All right, we'll get some examples. Don't worry. We'll get some. All right, so here is what it looks like. Here's what the Lagrange form of the remainder looks like. So the exact error, the difference between the function value, right, f of x, and the nth degree polynomial, this cap p sub n, so that's the nth degree polynomial. X is the value we're subbing in to that polynomial. Now that difference being absolute value, that reminds me of the format for exact error. So that whole piece on the far left is the exact error between the real function value and the polynomial expansion value, the estimate that we know has error. Well, that is going to be called the nth degree remainder, right? So r sub n at x, that is similar to what we looked at with alternating series error. That error, that remainder, is always less than or equal to, just to cover our bases. Here we go. The error term looked like the very next term in the series. So n's become n plus 1, so that's why we have n plus 1 factorial in the denominator. X minus a, the center, raised to the n plus 1. Now, that numerator is just the value in question, right? We're going to call it m, and we're saying that m is the biggest value. It's bigger than all the other values for that n plus 1th derivative between x, the point that we're approximating at, and a, the point that is the center. Whew. Yeah, I told you. I told you to buckle up. All right, you probably need to see some examples to like turn this dragon into a kitty cat. It's not as bad as you might be thinking, okay? So how do we apply the Lagrange form of the remainder? The whole thing can just be summed up into identifying the correct value of m, right? So if all the n values, they'll all be spoken for. You'll know what the center value is, like you'll know what the x value is, like everything is going to be spoken for except for that numerator m value. So I'll show you a couple of problems that the AP exam has thrown at you or thrown at students. So one came from the 2008 exam. That's a while ago. Okay. All right. So there's always a Taylor series question. There's not always Lagrange error. Like I told you, be praying for an alternating series error question. They're a lot easier. Now we're going to do this whole question. So we're given a table of values, h and h prime and h double, triple, and h to the 4th derivative of x, and then at different x values, we're given these values. All right, I'm not going to tell you what they are. You can see them. Now it says that h is a function where the derivatives exist for all orders. Now that means that it has an infinite number of derivatives. Well, that means that we can make a Taylor polynomial for it, and that only happens for x values bigger than 0. All right, well, that's okay because that's all we really care about. Now, selected values of h and its first 4 derivatives are in the table. All right, we figured that out. And then the function h and the 4 derivatives are increasing on 1 to 3. Now, that seems like a weird thing to say, but that's going to come in. That's going to come back in here when we do the Lagrange error part. So we're going to do each of these parts. All right, write the first degree Taylor polynomial for h about x equals 2. Okay, do that. So that is back to the general form of a Taylor polynomial. The nth derivative at the center divided by n factorial multiplied by x minus the center raised to the n. So if we just want a first degree Taylor polynomial, that just means we need 2 terms at most. We need h and h prime, that's all. So here is where I come up with that approximation. So it's h at 2, right? I call it p sub 1 because it's the first degree polynomial. So that is just h of 2 plus h prime of 2 over 1 factorial times x minus 2 raised to the first. Well, h of 2 just so happens to be 80. H prime of 2 is 128. Bada bang, slam dunk, we got it. All right, now we're going to use that first degree polynomial to approximate h of 1.9. We don't know what h of 1.9 is, but we're going to use the polynomial, that's their purpose, to approximate the value. So we're going to sub in, we're going to say that h of 1.9 is approximately the value of the first degree polynomial of 1.9. So plug all that in, get my approximation at 67.2. Now, is that bigger or smaller than h of 1.9? Okay, well, we got to think about this one. What were we told about all of the derivatives? We were told that all of the derivatives were increasing. That means like derivatives are positive. Well, if it means that all the derivatives are positive, it means that the function value is positive, and the first derivative is positive, and the second derivative is positive. Oh wait, that means the curve h is concave up. And what we have here is a tangent line, and the tangent line is always under approximating concave up curves. Therefore, 67.2 is less than the real value because the curve is concave up. And that's where that little last little sentence came in on the prompt. All right, so the second problem of this 2008 question is write the third degree Taylor polynomial for h about x equals 2. Well, we've already got the first two terms. We just need to add the next two. So that would be what we started with. So we already have that part. But just back to the Taylor series, general form, right? We want to do h prime, double prime at 2 over 2 factorial times x minus the center raised to the 2. And then the third derivative at 2 divided by 3 factorial times x minus the center raised to the third. Okay, so that is the general form of a Taylor polynomial, and then we just have to go grab those values. So h double prime is here, h triple prime is here, and we just have to sub those values in the right spots and simplify it accordingly. So there it is. There is the third degree Taylor polynomial, so p sub 3 of at x is this Taylor polynomial centered at 2. And then it says to use that polynomial to approximate h of 1.9. Approximating h of 1.9 again. This time we don't have to say anything about it. We're just going to approximate it. So h of 1.9 is approximately the third degree polynomial, which is equal to, I subbed it in my calculator, don't worry, I got 67.988. Okay, so a little bit bigger, right, than 67.2, right? Because we said 67.2 is an under approximation, so it makes more sense that the more terms I use sneaks me higher and higher. Okay, now, here we go. Lagrange error. All right, look back up there. Use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with an error less than 3 times 10 to the negative fourth. Go. Okay, so Lagrange error says, I'm just going to state the Lagrange error bound. All right, so back to that box where I give you the Lagrange error, the difference between the real value, h of 1.9, and the third degree Taylor polynomial at 1.9, that's the exact error. That's equal to the third degree remainder at 1.9. So that is always less than or equal to the absolute value of, now all those n's stopped at 3, so that means the next term has 4, so that's why it's 4 factorial. And then x minus c, 1.9 was the x, 2 was the center. So 1.9 minus 2 raised to the next higher value, so raised to the fourth. I told you all that was going to be spoken for. The only thing that's not spoken for is the daggone value of m. How do we figure that out? Oh yeah, that was the maximum value of the fourth derivative function between 1.9 and 2. So let's go back up to the table because it's gone. We need to figure out the fourth derivative. The fourth derivative. Which one of these values am I going to pick? All right, so we want to find the biggest value of the fourth derivative function between 1.9 and 2. Wait, it said that all the derivatives are increasing. So where is the maximum value on an increasing curve? At the endpoint. That's right. So the biggest value of that function on the interval 1.9 to 2 is going to happen at 2. So we've got that value, 584 over 9. So take that value, 584 over 9. That becomes the numerator of that error term. Bam! Got it right there, 584 over 9. Sub that in. Now just in the calculator, you get this value, 0.00027037. Guess what? That's less than 3 times 10 to the negative fourth, or 0.0003. We did it. Hallelujah, we did it. I don't know what we did there, but we did it. We used the Lagrange error form to say that the error was less than 0.03 over 10,000. All right, one more example. All right, I know your brain is fried right now. So in 2011, there was another Lagrange error question, but this time the information was given as a graph. We kind of zoomed in here, but hey, we'll deal with it. All right, so we've got a picture of the fifth derivative function's absolute value. What the heck, AP? What are you giving me that for? I don't know. Well, eventually we're going to get to Lagrange error. So we're given this function, f of x is sine x squared plus cosine x, and then we're given the graph of the absolute value of the fifth derivative at x. Now a and b, I'm not even going to talk about them, nor am I going to talk about c. I'm going to scoot all the way to part d and just hone in on this Lagrange form of the error. So here's what it says. Let p sub 4, you know what it is, it's the fourth degree Taylor polynomial for f of x centered at 0. Okay, so use the information from the graph that was provided to show this business. Okay, so what is that business? Looks familiar, doesn't it? It looks like it maps back to that box, what I showed you earlier about the Lagrange form of the remainder. P sub 4 at 1/4 is the approximation at 1/4 using the fourth degree polynomial. F of 1/4 is the exact value of the function at 1/4. So that difference being absolute valued means that that is the exact error. I have to use that graph to show that that error is less than 1 over 3,000. There's no guarantee. Why would they give me that fifth derivative? Because they want me to use Lagrange error. That's what they want me to use. Now, they don't specifically say Lagrange error, but we know what they're trying to do. We see beyond. All right. So we're trying to show this piece. All right. So I'm just telling you here what I just already told you. All right. So the p sub 4 is the fourth degree polynomial. F of 1/4 is exact. So this difference is the exact error. So according to Lagrange form of the remainder, here we go. This value that we're trying to show is less than 1 over 3,000. That is equal to the fourth degree remainder at 1/4. So n is spoken for, it's 4. X is spoken for, it's 1/4. C, the center of this polynomial, is spoken for, it's 0. So that means we're going to bump everything up. So 5 factorial, 1/4 minus 0, just 1/4, raised to the, bump it up to the fifth. That's all spoken for. The only thing that's not spoken for is the value of that numerator. How in the world, whoa, I just kind of totally erased it. What is that value of m? What is that? Well, that is the maximum value of the absolute value of the fifth derivative on the interval from 0 to 1/4. Okay, so if we look at the graph, right, we're going to zone in on that interval between 0 and 1/4. We don't need the rest of it. We just need the function between 0 and 1/4. So let me just blank out the rest. We don't need to even look at all that. We just need to see on this interval right here, what is the highest value of that graph? I don't know. It looks like what? It looks like 0, 20, 40, 30, maybe? See where that might be a problem? So you might be tempted to say about 30, right? Well, if it's about 30, right? Remember what I said earlier? There is an exact value. If we go too small, we blew it. If we go just a little bit bigger, we're still okay. So are we okay to go with 30? Do we know that 30 is it? No. Don't be tempted to say 30. You were tempted, but don't. So again, we want to make this error as small as possible. So we're going to know for a fact that the first value that I know that's bigger than that is 40, right? I know that that function is always less than 40 for all those values. I don't know that it's 30, but I know for a fact that 40 is bigger than all of those values. So we did it. We've done it. 40 is going to be that value I substitute in for m. So multiply it all out, simplify, I get that the 40 over 5 factorial times 1/4 raised to the 5th is equal to 1 over 3072. And folks, that's less than 1 over 3000, and that's what we needed to show, so we did it. If we go too big, then our error is actually bigger, or our error is bigger than 1 over 3000. If we go too small, remember, going too small doesn't help you, because if you make your error too small, you may not get the actual value. There's an exact value. We can go just a little bit bigger and that's okay, but we can't go smaller. So let's wrap it up. Not all series alternate, so there is another mechanism for determining error. That is called the Lagrange form of the remainder. And the Lagrange form of the remainder looks like that beast right there, where really the only decision you have to make is the value of the numerator, m. And the value of that numerator is the maximum value of that next derivative function between the value that you're approximating at x and the center of the polynomial a. And we definitely learned this, that alternating series error is way easier than Lagrange error. But I hope this video at least gives you an entry point into Lagrange form of the remainder. Don't be scared away from it, but certainly you can start wishing and praying for an alternating series error question on the AP exam. But if you don't, at least you have been prepped. All right, guys, that was a blast. Holy cow. If you're not a subscriber, you know what to do. Click the button. Don't even hesitate. Do it. If you want to watch some old videos, go check them out. And I'll see y'all next time. Peace.